I'm Anil Kumar, and here is a fresh look to Unit 3 Advanced Functions Characteristics of Polynomials. In this video, we are going to discuss the graph of power function f of x equals to x to the power of n, where n belongs to whole numbers. You will appreciate that polynomials basically are combinations of these power functions. So it is good to understand power function as a single unit. And then as we explore through this chapter, we will understand more and more characteristics of polynomials. To begin with, the power function f of x equals to x to the power of n is defined so that n is a whole number. That means n could be equal to 0, 1, 2, 3, and so on. So depending on the value of n, we'll have different type of graph. We'll sketch these graphs and then find similarities or differences between them. That is going to help us to understand polynomials better. So let's begin with n equals to 0. And then we'll take n equals to 1, 2, 3, 4, and so on. So if n equals to 0, then what is f of x? In that case, f of x equals to x to the power of 0. And what is x to the power of 0? It is 1. So f of x is 1. It is a constant. When we say f of x equals to 1, that means for any value of x, the value of f of x is 1. So it's a horizontal line with y-intercept of 1. So that is what is the function when n is 0, right? So it's a constant function. It doesn't change. Rate of change of this function is 0. It does not have any x-intercept. How about its range? Range is just number 1, the constant value of this function. Range is also not from negative infinity to positive infinity or anywhere in between. It is just 1, right? This is a very unique characteristics of a polynomial, and normally the characteristics which we talk about are very different from this. You will see soon. Now if we consider x equals to 1, then how the graph will look like. Let me sketch it here. If n is equals to 1, I should say, in that case, f of x is x to the power of 1, which is x. So that means y equals to x. We get graph of a straight line which diagonally cuts across the plane and divides it into two equal parts, right? Now this is also a straight line. There is no smooth curve here involved. So in these two ways, it is actually different from normal polynomials, right? But this particular power function is quite similar to polynomials in a way that it exhibits most of the characteristics which a polynomial does, right? Now let us explore those characteristics, and those are when the value of n could be 2, 3, 4, 5, and so on. So for that, what I will do is I'll divide my page into two parts, and I'll consider the values of n in one where n is even, and in the other when n is odd. Since even and odd degree makes huge difference, and there are lot of similarities between these two groups. So let's explore these two groups. We'll take different values of n and sketch a kind of graph for them. So the first one, let us take n equals to 2. So if I take n equals to 2, then we have the function as, let me write function here, x square. x square you know is a parabola, right? So we could sketch it like this. Okay, now let us consider n equals to 3. Since 3 is odd, I'm writing it at this place. That is x cube. The graph for x cube is kind of like this. Now how are they similar? Well, right side is up to infinity. Now domain is all real numbers, smooth curve, right? Going through origin. Well, so there are so many ways they are similar. Now what happens as the n value increases further? That is to say, if n equals to 4, that means x to the power of 4. How will this graph look like? It will be quite similar. Let us say this is the point 1, 1. Let us say this point is 1, 1. Then 1 to the power of 4 or 1 to the power of 10 is 1, correct? But if we have a value where x value is greater than minus 1 or plus 1, in that case, higher exponent will give us higher value and a lower exponent will give us lower value. So what really happens is that as n value increases, the graph becomes flatter here and steeper in this portion, but it will cross through 1. Do you see that part? Same thing happens here when n becomes equals to 5. It becomes x to the power of 5. Then this portion becomes flatter, right? You know, 1 cube is also 1, minus 1 cube is minus 1. So those are invariant points, or you can say similar points, right? So the graph becomes kind of like this. So it's very important to understand this aspect. So we are saying that this point is 1. 1 and here minus 1. Now as the n value increases further, that is to say, if I make it, let us say, n as 10, then it becomes x to the power of 10. The graph basically becomes more flatter here and more steeper, right? So we are having a very close look at it. So it's not vertical, remember that part. The only thing we are saying is becomes more flatter and more steeper. That is what we are trying to understand here, correct? But basically all of them are very similar, right? So generally when we say a graph of polynomial, then we are saying like this. We see a smooth curve which is continuous all along the domain. Domain is all real numbers, and the end behavior is, that is, when x approaches infinity, y approaches infinity. If x approaches negative infinity, y may approach positive infinity or negative infinity depending on the degree, right? We say when the degree is odd, it faces opposite ends. When degree is even, it faces same end. Do you see that part? Now, when we talk about polynomials, then what is a polynomial? Now let's define that. So we'll say a polynomial is combinations of these power functions. We can write this as a n x to the power of n. Sum of these where n value changes from 1 to n, right? So when we expand that, we could write this as a n minus 1, x to the power of n minus 1, so on till like a2x square plus a1x plus a0. Now that a0 is a constant. In our case it came to be 1, right? Anyway, the functions which we considered are power functions with coefficient 1. Now in this polynomials, we could have any real number as a coefficient, as you can see. But basically each term in the polynomial is a power function. So depending on which combination we have, we'll have a graph for that. And the characteristics of polynomial will be defined because of that. Now, whenever we're talking about end behavior, the term with highest degree plays a major role. End behavior is decided by the term which has the highest degree or the exponent. That highest exponent is also the degree of the polynomial. So combined with the coefficient of that term, we find the end behavior, and this term is called leading term. We normally use the term leading coefficient. Let me write that first. The coefficient of the variable with highest degree is the leading coefficient, right? Now, if the degree, that n highest value, is even, then the graph of the polynomial will look like this as far as end behavior is concerned. So what I will do here is, for end behavior, when the degree is even, it will be like this. That means both on the same side. But when n is odd, it will be in opposite ends. If the leading coefficient is positive, right side is up, as we have. But if the leading coefficient is negative, right side will be down. So for odd, it will flip. Opposite ends, right side down. But for even, both down, if the leading coefficient is negative, right? So with these combinations, we have different kinds of polynomial characteristics. We'll explore this as we move on, but do remember that we have exception to these rules. Constant function. If n is 0, range is restricted to just one value. It does extend from negative infinity to plus infinity, but the range is also limited, and it's not a curve, it's a straight line. It is a straight line even when n is 1. However, this particular linear function exhibits most of the characteristics of the odd functions, including odd symmetry, right? Even functions will have even symmetry, can have, I should say. A power function with even degree will always have even symmetry, but when you combine these, then they may lose their symmetry, right? So we have to figure it out. But I think with this, we are good to go for understanding the characteristics of polynomials in general. But remember your base power function. It helps at many places to decide the characteristics of a polynomial. I hope you appreciate it. Thank you and all the best.